Professor Menon, if we can start, if you would like to describe for me your current role in the science advisor in the government, would you just describe to me your current role?
Well, presently my designation is science advisor to the Prime Minister and member of the Planning Commission, Government of India. I am also a member of the Atomic Energy Commission, and in that sense I am connected with the nuclear program of the country, and of course in some sense I have had a link with it from a little over 30 years ago when I returned to India from England, where I was doing research, and joined Homi Bhabha.
Can you tell me something about those early days? What was the feel, the atmosphere at the time among the young scientists in India?
Well, as far as the atmosphere was concerned, it was certainly a very exhilarating one. There was a sense of elan because Homi Bhabha was a very dynamic figure. He had many qualities. First, of course, one is aware of his background as a theoretical physicist. He did some spectacular work during the 1930s and 40s, primarily related to cosmic rays, elementary particles, high energy physics, and the theoretical aspects of these fields. And I have no doubt that he was one of those who, had he continued to work in pure science, would have won a Nobel Prize. So he was in that category as a physicist. He was, of course, also a person with very broad interests. He was, as many are aware, an artist himself. He used to do exceedingly good pencil sketches. He did paintings, very interested in music, interested both in aspects of art from the West and from India, and in general one of the individuals whose interests covered both science and the humanities, extensively traveled, and a very wonderful conversationalist, a very dynamic leader.
Who were his mentors?
Well, Homi, of course, had his early education in India, that is in the sense of school and the early stages of college, but went to Cambridge at a very impressionable age. And he was at the University of Cambridge in perhaps one of the finest periods for physics in Cambridge, the days of Rutherford, and of course the great theoretical work of men like Dirac, and a place where one interacted with people like Kapitsa and Blackett, the whole range of people who were around in the Cavendish laboratory in the 1930s. And apart from that, he traveled around in Europe. He spent time at Zurich with Pauli, in Rome with interacting with Fermi, in Copenhagen with the Niels Bohr School, and so he had quite extensive contacts with all that represented some of the finest in physics of the 1930s before he came back to India. War broke out, and therefore he stayed on. Otherwise, perhaps he would have gone back to Cambridge, gone back to Europe or America, and maybe continued with his science there.
Could you describe his chief contribution to India's atomic energy program?
Well, perhaps the most important element is the fact that he envisioned it. And that was, I think, quite a remarkable story, in the sense that he was working in Bangalore, continuing with his pure research, largely mathematical, and some experimental work relating to cosmic rays, when he thought that it was important to set up in India an institution, a program of work in what he felt were the really modern, rapidly developing areas of science, which is really modern theoretical physics, quantum mechanics, nuclear physics, studies relating to high energy physics and elementary particles, cosmic rays, and so on. And that is when he wrote his now famous letter to the Tata Trust. And in particular, there was a letter which he wrote in March 1944. And this was, as you know, well before the world got to know about the Alamogordo test or Hiroshima and Nagasaki of 1945. And in that letter, he had even stated, and I would quote from it, that when nuclear power comes about, India will not have to look abroad for its experts. So in a certain sense, even in 1944, he had envisioned the possibility of nuclear power and the fact that if we were to take advantage of this new possibility, we would have to have enough manpower, experts. And if we set up institutions in these areas, then one would generate these experts and would have them available. So that was the beginning of the Tata Institute of Fundamental Research, which was actually set up in 1945 and became, as Dr. Bhabha called it, the cradle of the Indian atomic energy program.
Now, what other visions did he have for India's nuclear program? I always think of the 3 steps in the development.
Well, I think his basic concepts were very clear. The first, that power, energy, was essential for development, and he traced the manner in which the development in society was closely related to availability of energy in society. Second, that as far as India was concerned, it had a very low per capita consumption of power, which is about 18 kWh in 1950, a total power generation of about 2,300 megawatts. And he said that at this level, you will never have real modern development. Therefore, India's need, apart from everything else, was to ensure that more energy was available for all purposes, industry, agriculture, services, and so on. He also showed that this increase in power availability could not come about by dependence on coal alone or even on hydroelectricity, because India did have fairly large reserves of coal, but when you considered it in terms of per capita availability, you only had something like about 100 tons. Similarly, India has fairly large hydel potential, and only a small fraction of it was tapped at that stage. Even then, one could show that a large part of the untapped hydel potential was in difficult areas. So one could more or less estimate how much you could get from coal and from hydroelectricity. And at that stage, India didn't have too much in terms of its own oil and gas availability. Though of course it has more of it today. We use it for other purposes, but not for what one would call power generation. That is why he felt that this new source of power, this new potential of nuclear energy, should be exploited to the full. And he felt that this could be done in a succession of steps.
Can I just stop you there? Is it possible just to summarize that? What you've, all the 3 steps, the 3 explanations you've just given for why he was supportive of nuclear energy for India. Is it possible just to make it a bit briefer that India was energy poor.
Oh yes.
And yeah,
You want me to go back on that?
Yeah, just a little. If you could just summarize it a little.
Bhabha was convinced that energy was essential for development. At the time, soon after independence, when he was writing about these issues, India had a per capita availability of 18 kWh of power, and this was extremely low. And his thesis was every effort should be made to rapidly increase this availability. He also showed that whereas India had large reserves of coal, the per capita availability, because of the large population, was only 100 tons. There was hydel power available, a large part of it in very difficult areas for exploitation. And he therefore felt that the new potential of nuclear energy should be exploited to the fullest.
So what were the goals then of this early atomic energy program, and how did you set out to accomplish those goals?
He felt that in the first instance, one would make use of the uranium that is available in the country. India does have uranium, and one would therefore have what would be familiarly called uranium burners. But these reserves were limited. Therefore, one could not go with a very large program on a long-term basis. So the next step would be to proceed to breeder reactors where more fuel was generated than consumed. And the third step would be to make use of the very large and abundant thorium reserves of the country, because then one could convert the thorium-232 to thorium-233, which would give rise to uranium-233. And uranium-233, like uranium-235, is basically the material for power generation.
How supportive was the Prime Minister Nehru, to his visions for nuclear energy?
Well, from the beginning, the relationships between Homi Bhabha and Jawaharlal Nehru were exceedingly cordial, and Nehru had the fullest trust and confidence in Homi Bhabha and supported his programs fully. And Bhabha has paid very rich tributes to the support that he received from the Prime Minister right from the time India was free until Jawaharlal Nehru's death in 1964.
If you had to sum up Homi Bhabha's legacy, how would you describe it?
His legacy was essentially in terms of the fact that in what was regarded as an extremely complex, sophisticated, newly emerging technology, he had the vision to embark India on this, and he had the courage of his convictions, and he was able to generate a spirit of self-confidence, particularly through the very large numbers of those imbued with his vision, with his sense of self-confidence and self-reliance, which form today not only the scientists in the atomic energy program of India, but across, who have spread out into many other programs, such as our space program and other areas of science and technology.
Would you describe him as one of your own mentors in that sense?
I would say yes, in a sense, though I didn't directly do research with him in a formal sense, but I certainly interacted very closely with him, and there's a great deal I learned, particularly his spirit of self-confidence and dynamism, and of course a great deal of physics, no question about it.
How did India benefit from Atoms for Peace?
Well, as you know, the conference was a very large conference with very extensive international participation. Homi Bhabha was the president of the conference and gave both an outstanding presidential address as well as in his summing up. And he said a great deal in it, though unfortunately many people remember what he said at the conference in terms of his prediction that in a couple of decades one would be on the verge of having abundant thermonuclear energy. But however, a large part of what he said related to the need for energy and the need for international cooperation, the fact that once knowledge becomes open, it can never be taken back. And very large numbers of our scientists participated for the first time in this major conference on the possibilities of nuclear energy as a principal source of energy, particularly for countries like India.
How did that international cooperation manifest itself in the atomic energy program in the early days? I'm thinking of the Saras reactor and the Tarapur and so on.
Well, actually, there was very significant cooperation in the early days of India's atomic energy program. This arose principally because one was in the period after the Second World War. There was a general euphoria relating to science, technology, the fact that never again did the world want another war, and we should do everything possible to rapidly bring about development and so on. But apart from that, there was also the feature that Homi Bhabha had friends all over the world. And in fact, many of the leaders of the atomic energy programs in the US, in Britain, in France, in the USSR, and so on, Canada, were very close friends of Homi Bhabha. So large numbers of our scientists trained in Saclay, at Harwell, at Oak Ridge, at Argonne, at Chalk River, and returned. And similarly, we had scientists from abroad who worked in the Indian atomic energy program. And therefore, it was really a program in the right sense of international scientific cooperation.
Were you present at the openings of the Sarasvati Center?
Yes, I was there at the various occasions, like when Apsara, the first swimming pool reactor, the various occasions relating to the Cyrus reactor, the uranium metal plant and fuel fabrication facility, to the plutonium plant, various occasions that you referred to.
Do you remember any particular memories of those openings? Any anecdotes you can tell us?
Not anecdotes as such. Of course, perhaps the most interesting event in that sense for a public affair was the fact that when the plutonium plant was to be formally dedicated, after all, everything was more or less finished, they forgot that the actual plaque had to be unveiled, and which the Prime Minister had to do. And so they had to go back, and so that was an amusing slip-up, which I remember, a large audience. But one important feature about most of those occasions was the fact that Bhabha was the sort of person who delivered and then spoke about things, and usually did things ahead of time. It's not one of those who kept announcing what he would do in that sense of the word. He was a very good example of delivering the goods, so to say.
I realise we're backtracking a little, but can you just explain, just really briefly, why India took the step, made the decision to go ahead with reprocessing at what seemed like an early stage? That was the end of the 50s, the decision was taken. Can you explain why India took that decision?
Well, I think Bhabha's papers clearly bring out the importance of having plutonium or enriched uranium. And he has clearly also stated in his papers, right from the beginning, that any enrichment process which would have to proceed along the then known diffusion barrier technology would be very expensive, certainly would consume an enormous amount of power, and plutonium was produced in a reactor, and so large quantities will be produced in power reactors. Therefore, you could extract the plutonium and then make use of it for further steps along the power production route.
Plutonium, as I understand it, can be used for two purposes: the civilian purpose, and then there's the weapons purpose, the military purpose. Can you explain to us the difference between the technology involved in those two?
Well, we are all aware that when the first bombs were made in the Manhattan Project, one was made of plutonium and the other was made of uranium-235. And therefore, it is known that if you want to make nuclear explosive devices, you certainly need one of these materials, or you can, of course, use uranium-233 also. The basic point is uranium-235 is something which you would have to produce, as I said a little earlier, in terms of isotope separation technologies. And this would mean special plants, large consumption of electricity. It's expensive. As far as plutonium is concerned, it is produced in a reactor system, and therefore you can extract it. It is a chemical extraction. And if you extract, you can use that plutonium as part of the nuclear power cycle. And therefore, it is something which is part of a regular nuclear reactor program for electricity generation. Now, of course, these are materials which can be used for producing nuclear explosions. And for that, of course, one has to use completely different technologies. I mean, a reactor is something where one is concerned with having a chain reaction on a controlled basis from where you extract the energy and then convert it to electricity. In the other, it's an uncontrolled reaction which leads to an explosion.
Is that okay? The hand, oh, sorry, you can't see. Just watch your hands, and I shouldn't have given you those to play with.
Oh, I'm sorry.
No, but if we get to now, I'm just thinking now.
Is there
I think
something?
it's okay. How can you just explain to us how a crude device is actually built? What do you need in order to build a bomb?
Well, that's a question which is difficult to answer in terms of any details. All I can say as a physicist is with regard to the basic principles involved. The basic principles, as everyone knows, is that we have the fission process, and in the fission process you generate more neutrons. That's a neutron coming in will induce fission, and in addition to fission there's more neutrons which are produced. So these can then produce more fissions and more neutrons, and this is what's called the chain reaction. Now, in the case of a reactor, since you need a control system, these neutrons are normally moderated, slowed down. In the case, of course, of so-called fast breeder reactors, one is dependent on the fast neutrons and not on the slowed down slow neutrons. In the case of any explosive device, one allows the chain reactions to go ahead in rapid succession, so that each chain reaction which results in each element in the chain reaction which results in a fission and neutron production will lead to more fissions and more neutron production very rapidly. And this is what one would like to have. So for that, one clearly requires a minimum mass of the material. because otherwise soon you'll have the neutrons going outside the mass and escaping into the air. So one wants to make use of them, so you need adequate mass for the purpose and adequate number of nuclei which can be fissioned. And there is therefore what is called a critical mass for this purpose. And once you have the critical mass, then of course you would have enough succession of steps which take place in this very rapid fashion, which is essentially a runaway process resulting in an explosion, because then you would have had enormous amount of energy generated in the process.
How many countries have the know-how and the expertise and the materials to manufacture such a bomb?
Well, this is again a very difficult question. We know of the countries which actually, there are, as you know, the so-called weapon countries as defined by IAEA and so on, which essentially is the USA, the USSR, Britain, France, and China. And these are the nuclear weapon countries. They have actually produced bombs and have bombs available for use. Now, with regard to other countries, there is a great deal of technical expertise in a whole range of countries in the world in terms of basic physics, namely to know about all the things that I just mentioned, namely what constitutes a critical mass, how do you moderate neutrons, how do you calculate various aspects relating to neutron behavior in solids and so on and so forth, and a whole lot of associated technologies in nuclear physics, in neutron physics, in bringing material together and so on and so forth. But it's very difficult to say the final details of technology which any country possesses to produce an explosive device, or for that matter, as you say, a bomb.
Give me a second. I understand the process. If I put it here? I understand the process. I still don't think we've quite got across the business of the materials. And I like the way you did it before, the way you described the critical mass. And I wondered if we could reenact that.
Material.
The way you use these to describe how you get a critical mass. If you could just demonstrate how you get a critical mass and the materials you need in order to make a bomb, as opposed to generating power, what the difference is again.
Yeah, of course. Okay.
Okay. Are we ready? Are we ready? Okay, good.
Now, what point did you want me to start on this?
Well, just from the beginning, but just a little briefer, and try not to say, as I said before, because that makes it difficult to edit.
Mm-hmm. Okay.
Okay, if you could explain for us again.
Well, as you know, the basic principle in the case of reactors, of nuclear explosions and so on, is the nuclear fission process. And we are aware of the fact that in a material such as uranium-235 or plutonium, what happens is a fissioning. If you have a nucleus, for instance, that nucleus breaks apart, and this is called a fission process. When it breaks apart, it also releases neutrons, and there's an energy release. So the fission process implies the breaking apart of a nucleus, the release of neutrons, and the release of energy. And these are the elements which characterize it. Now, if you have a mass of this material, these neutrons will go into further nuclei, produce further fissioning. Further neutrons are emitted, and with some energy release. And this goes on. Now, in the case of a nuclear reactor, you are dealing with a controlled system, which implies that the neutrons are slowed down, and you have slow neutrons, and this is done using moderators like, for example, water, light nuclei, water, carbon, and so on can be used for the purpose. In the case of fast breeders, you're using the properties of fast neutrons. but they are all under controlled conditions. And you also have control rods in it, so that if there is any excess activity, the control rods are brought in and they can absorb the excess neutrons. Now, in the case of, for example, the physics of any explosive device, what would happen is that these neutrons which are produced through the chain reaction, which is a fissioning, release of neutrons, they go into more nuclei, more fissions, more neutrons, and this is called the chain reaction. This takes place very rapidly. And when it takes place rapidly, you will find that there's an enormous amount of energy released. But if you have only a very small mass of the material, the neutrons very rapidly get out into the air and escape, and there's no more fissioning, no more chain reaction, it all stops. Therefore, you do not have a real explosive process. If you have enough material, it's a large amount of the material, then quite clearly there can be enough succession of fissions, neutron releases, more fission, the chain reaction, energy release, in order for it to reach explosive proportions. But quite clearly you can't have that amount of material just kept, because then you could have an explosion. I mean, even due to a variety of accidental situations. Therefore, quite clearly, nobody would keep explosive material above a critical mass together. It is kept as separate pieces. The question is, how does one bring it together at the time when required? And one of the well-known things which have been defined is to bring separate pieces of matter together so that it is brought into the critical mass. And this is one of the well-known things which are described in the so-called textbooks many talk about with from the viewpoint of nuclear explosions. But there are many elements in detailed technology which go into all of this, and this is what most of these nuclear weapons establishments presumably work on. And that is the reason why they continue to refine these and have more and more tests on a continuing basis.
So is there still a secret part to all this?
Depends what one means really by a secret part to these things, because as you know, there are many nuclear weapons countries today, and one knows the basic physics, if you wish, or the basic technical aspects which underlie all these, whether it's a reactor or a nuclear explosive device. The main point about most of these things is having all the detailed information and being able to do what is essentially a very sophisticated technical experiment. So if one can do a complex experiment in physics, one certainly can do these things. But you need to do those. There are many detailed properties one needs to know in all of these cases.
Where does India fit in? Oh, I'm sorry.
That critical mass removed.
Okay, thanks. Okay, good. Well, thank you. That was our little lesson in physics there. And we'll get the chance to just have diagrams as well to explain, but I just wanted to get the point across. Now, if you can explain for us the PNE for the 74, not the decisions which were taken because you weren't privy to those, but again, scientifically, what happened? What was the technology involved there?
Technology, in what sense?
In the what was the PNE? What happened essentially?
The PNE carried out by India in 1974 was essentially carried out below ground, and it was to measure the nature of phenomena which would take place when one conducted such an explosion, in terms of the fracturing of rocks and the detailed aspects of what happens to the ground. Because as you know, peaceful nuclear explosions can be used for many purposes where you need single large amounts of explosive power. And this is essentially for cratering purposes, for canals, river diversions, and things of this nature. So one would like to understand what really happens when a very large amount of explosive power is actually delivered. I mean, how does the ground behave, the geology, the details of it, and this was really the experiment conducted in 74.
And was the explosion itself similar to a bomb? Was it a bomb explosion? What was the difference?
Well, the point really about these things is it was an explosion, and the target or objective in this particular case was to understand
how it differed from the... Yes. Okay, good. Good? Yes. How it differed from the old subject of the bomb.
Well, I think basically the objective in the case of the peaceful nuclear explosion conducted at Pokhran in 1974 was clearly to try to understand the phenomena relating to how the ground behaved in terms of cratering, in terms of solidification, and so on and so forth. And therefore, what are the aspects one would have to know about in terms of using it for any purposes which involved geological work, as I said, in the case of oil, natural gas, river diversions, blasting, which involved very large explosive power. Now, when you really talk about a bomb, you are talking about an objective which is a destructive purpose, where you want to deliver energy in a certain way, which can either be blast energy, it can be heat energy, it can be radiation from the radioactive materials and so on. And also you try to partition between these forms of energy and then consider what the delivery system is, which may be an explosion in air at various heights above the ground, which may be an explosion on the ground itself, and therefore it is in relation to a target, an objective, and you are also concerned with certain types of efficiencies in performing a certain end task. So therefore it's a very targeted, very specific objective of energy release in this particular form.
The technology, however, is the same. Is that true?
Well, as I said, the basic physics in all of these things is the same. But when you talk of technology, you have to relate it to the end objectives, and therefore you specifically have to say you require a certain efficiency. And for example, take what was dropped over Hiroshima and Nagasaki, which is the two examples we know of actual nuclear bombs which were used over targets. They were to be carried in aircraft, so therefore they had to be related to what an aircraft would handle in terms of size, in terms of everything related to it, and so on and so forth. So similarly, you could, for instance, have an explosion and only have 5% efficiency or 10% efficiency. You may have 70% efficiency. All these details come into the picture in relation to an end objective. And so technology is really something which you must relate to what your end objective is. The physics is common in all of these. They all arise from the same materials, whether it's plutonium or uranium-235. It arises from the chain reaction. It arises from a non-controlled versus controlled. You're dealing with critical mass. These are all common elements of scientific terminology or principles which apply across. But there are differences in end technologies in terms of what your objectives are.
That's very clear. The case of Pakistan, in the last few years, they've mastered uranium enrichment, and they say this. What are the implications of this? They say 3%, 5%. What does this all mean? Does it mean they can produce a bomb? Should we be worried about Pakistan's capability?
It's a very difficult question to answer. All I would say is, you said about enrichment. As you know, in the case of enrichment, you need a certain degree of enrichment That means a certain proportion of uranium-235 in the total uranium, and this is relatively small degree of enrichment when you want to use that in nuclear power generation. But when you want to use it for explosive purposes, such as a bomb, you have to certainly ask for much higher degrees of enrichment. Now, I have no knowledge, no information with regard to the specific aspects of enrichment carried out in Pakistan, the degree, how far they have got to, except newspaper reports and various claims which have been made, which are also published in the newspapers. But the fact of the matter is that once you proceed along that pathway to enrichment, you certainly finally land up with material, and this material, uranium-235, is basic material with which bombs can be made. So one is concerned about proliferation.
If Pakistan was to go ahead with the test, what do you think, what would be India's reply to that, do you think?
That's a very difficult question to answer, and certainly not an answer I would like to give, because it really is a political question, and which would have to be dealt with by those concerned with political policy making.
Sure. Let's just stop a second, because you were making the point.
I was trying to make is...
You ready? Yeah.
The basic point I was really trying to make is that it's very difficult to keep aspects in science really secret for too long. There can, of course, be lead times available, in the sense that someone has a discovery or someone has...
Let's just do that again.
Yeah. The basic point I was trying to make is that in science it's very difficult to keep things secret for too long. There can, of course, be lead times, lead times which can be measured in months or even years for that matter. But at some stage or the other, people who are determined, working with a very definite objective, will, through basic scientific principles, arrive at the same place. And this is rendered enormously easier if you know it's been done before. Of course, fact is, if you're doing it for the first time, then there is a problem. And this is about, the same question about the nuclear bomb area. What was really remarkable was the fact that the Manhattan Project succeeded so magnificently in that time frame, and the very first test at Alamogordo was successful. That was remarkable. And in fact, two objects prepared, one a plutonium-1 and one uranium-235-1, both dropped unfortunately over Japan, Hiroshima and Nagasaki, both worked. But afterwards, once it was known that these things existed and this worked and this is the route, it is only a matter of time before anyone determined to do it. The Soviet Union was determined, did it. Britain was in the know-how, did it. France did it. China has done it. And any other country with really good capability in what I would call advanced physics experimentation and all the instrumentation and things which go with it, can do these things. Of course, there's a great deal of chemistry and so on. I am not restricted to physics.
So perhaps some of the Carter legislation was somewhat misguided then, the idea of being able to control proliferation by technical means, by stopping supplies and exports.
Yes, I think these can only serve a purpose in a limited sense. If one is concerned about months or weeks or years and so on, but not really in the long term. And I think in the long term, when people are determined, they'll manage to get the information. You cannot really keep knowledge back.
Can I just ask you about the origins of the Indian space program, what it set out to achieve and what your involvement was?
The Indian space program was, of course, obviously triggered by the fantastic event of 1957, the Sputnik, and the excitement of it. But the very first element was, of course, a feeling amongst people working in cosmic rays that instead of having to do experiments on the ground, looking at the universe like a frog sitting at the bottom of a well, we can now get to the surface of the well and look out and see things in a much clearer fashion. And therefore one could get out on rockets, on satellites, and do all these experiments. But Vikram Sarabhai, who was one of the cosmic ray physicists and was working with these ground-based experiments, had also visions of the applications which were inherent in any such effort. And this, I think, is very fundamental and important. India, as you know, is a large country, subcontinental dimensions. And when you really look back, when one was envisioning the space program, you straight away see a picture of a country with practically no broadcasting system other than at a few places, the big urban centers. Telecommunications also restricted to the big cities or smaller towns if you wish to, and so on. Now suddenly you have the possibility of satellites, and then of course the question of geostationary satellites that came on quite rapidly. Mid-60s, one could start then talking of telecommunications, of broadcasting, particularly television, on a national basis, and reach out to every point without disadvantage when viewed from the geostationary orbit. And of course remote sensing, to be able to look for many, many things, whether it's mineralization, pollution, forest cover, agriculture, water resources, snow melt, forestry, anything you wish to, from this vantage point. And therefore that became the basis for pushing ahead with a major space program. The very first things done in space were in terms of science experiments, the first rockets and the first experiments and so on. But it rapidly got converted in a few years through this vision of Vikram Sarabhai of the use of space technology for development. And in a sense, this has a great analogy with the vision Baba had of nuclear power for development.
Where were you in July 1980 when the test, at the time of the test? Were you directly involved with that, the SLV3 test?
The satellite launch vehicle?
Yes.
You mean from the... Yes. You mean the launch at Sriharikota?
Yes.
No, I was not there.
You weren't
No, I was not
involved.
physically at
No.
then. No.
No.
I mean, these are matters where it makes very little difference whether you're physically on the spot or not.
No, I just wondered if it felt like a period of great achievement, if you felt a sense of achievement and pride in...
Yes, it is. Every one of those was. I mean, I certainly remember, the first satellite was built, it was launched by the Soviet Union, the Aryabhata. And it was satellite built, completely designed, fabricated, built here. And it worked. So each one of these is an achievement. Of course, you don't have to be physically there. That's only more, if I may say, like a tourist. You can have always an interest in the matter.
People always refer to when they're concerned about proliferation, there's always a reference to the delivery potentials, the capabilities that India has as a result of its space program. Could you comment on this? Does India have military designs in terms of its space program?
You see, the main point is this, that one has to recognize that if one goes back in history, if you look at every single sentence which has been written, I mean, I can quote you chapter and verse on what Baba has written from 1944 onwards, and you will find there was not one sentence in it relating to nuclear energy being used other than for peaceful purposes. Throughout, the one thread that runs through Baba's papers is the manner in which one would generate more energy for development. If you look at everything that Vikram Sarabhai has written on the space program, and that is basically what underlies our space program, you will find the feeling of excitement on using space for development. The new opportunities which have never existed before, whereby one can transform. One does not have to go through the pathway everyone else has gone before, but use this new opportunity to leapfrog into the future. That's what lies with it. But quite clearly, anything can be used for destructive purposes. There's no question about it. I mean, certainly all capabilities relating to rocket systems to put satellites into orbit can be converted into missile systems. All capabilities relating to the physics and technology of chain reactions and fission and producing uranium or plutonium or whatever it is can be converted to essentially explosive purposes. There's no question about it. But those are two sides of a coin in any case. But India's purposes have been very clearly defined. And let me just ask a reverse question. If India's intentions really were to make these, and in principle we conducted the peaceful nuclear explosion in 1974, it's the first, and now we are in 1987, and a second has not been conducted. Does the world have an explanation for it?
That's a very good place to end. But let's just hold you there for just 1 second. How much tape, please? How do you envision the next 10 years in the nuclear age?
You're talking of the world as a whole?
The world as a whole and India.
I think we are at a very difficult stage from the viewpoint of the whole nuclear area for multiple reasons. One, of course, there is at the moment in many parts of the world as a result of Chernobyl, question relating to safety and safety aspects of all types. There are those who are, of course, afraid of the whole the Greens, if you wish to, afraid of the nuclear area in terms of radioactivity, contamination, accidents, minor nature, and so on. Others who are even afraid of it in terms of what might happen if, even in the case of a conventional war. We are seeing wars all over. For instance, one has seen in the case of the Iran-Iraq war, bombing of cities and so on and so forth. Now, if these had nuclear reactor systems and they were bombed, what would happen? Things of this nature. There are many questions. So people are very disturbed about it in the general sense of it. On the other hand, I think one sees from many countries, certainly France, Japan to the extent it can possibly go, the Soviet Union, proceeding still with nuclear power on a very significant basis. But these questions will continue to be raised on safety, on hazards, on accidents and so on. As far as the nuclear weapon scenario is concerned, we have certainly got to an overkill situation which is grossly over all limits. And one is in a very, I think, catastrophic position at the present moment, particularly from the viewpoint of anything happening which could be by error, accident, wrong decisions. And one should make every effort to wind down, to go back. And this must be done as early as possible, because one just cannot afford the risk of anything which corresponds to a nuclear exchange or a holocaust. As far as India is concerned, in spite of what I have just mentioned to you about the questions of nuclear safety and so on, we are proceeding, as you probably are well aware, with a nuclear power program. The target is to reach 10,000 megawatts of nuclear power by the year 2000. And this will be in a total power production in the country of around 100,000 megawatts. So about 10% from the current figure, which is just under 3%. So we are proceeding on increasing the percentage of nuclear power in the total. And this is essentially because we need to increase power availability, energy availability in the country. We are at such low levels still today from the viewpoint of any developmental activities. And we still believe in the basic principles which Baba had talked about, namely that energy is the key to development. And we know that energy is available through all the conventional means, thermal. We don't have oil certainly for burning, it's only coal. Hydel, we are tapping it, and it's needed for various purposes like plant load factor in terms of peaking load and so on and so forth. But where do we get all the power we need? We're also proceeding along the pathways many others would advocate.
What are the risks in terms of terrorists actually obtaining plutonium and making a simple device?
Well, I mean, certainly the risks are there of sabotage in nuclear installations, and certainly there can be thefts. On the other hand, they're making, in the sense of any ad hoc group, making nuclear devices out of this are not very great. But the risks are certainly there, there's no question about it. And we will have to certainly keep that in mind as the world develops and one has more and more availability of nuclear materials. But on the other hand, one can also say that it'll be certainly something which is very untoward if an event like that took place, which could be a small explosive device. Nobody would want to see that happen. But it's a very different scenario from anything which would involve a nuclear exchange between the superpowers. That is really the end of the world in many, many ways. Not only in terms of the 1,000 million or more directly involved, and whether you believe in the nuclear winter scenario or not, the fact remains that such a nuclear exchange may trigger off ecological reactions which may be totally irreversible. And I think all the evidence so far is that they would be quite hazardous. How disastrous, for how many, may be a matter which is debated, but certainly quite disastrous.
I should just ask you, we talked a lot about Nehru and Baba in the early days. Did Mrs. Gandhi share the same views about nuclear energy as her father? Was she as supportive of the nuclear industry as her father?
She was fully supportive of the whole atomic energy program of India, and she subscribed to all these facets, namely that India needed power, nuclear power would be one means, not the only means, but one and important means of ensuring that India did develop rapidly and get the necessary power needed for this purpose. But I'd like to remind you of a statement she made when she was at what is now called the Indira Gandhi Center for Atomic Research in Madras. And she said then, I don't remember the exact quotation, but something to the effect that what we want is not to make deserts, but to make the deserts bloom. And that was a hope in the nuclear energy program.